welcome to today's lesson on stretches of trigonometric functions. Last lesson covered how to graph the base trigonometric functions in radians. So start off, we'll look at what the graph of sine of x looks like. One thing to sort of highlight about this function, since when you evaluate sine of x at x equals 0, your y value is 0. So notice we have a point to start off with, at least right at the origin. Having looked at the and built the table of values for sine of x and cos of x in the previous lesson, we've looked at how to generate the y values that are here. So the progression for the graph of sine of x, if we use the origin as sort of the start of a cycle, the function starts to gradually work towards its maximum point first. So you'll notice the maximum value, the maximum y value, is 1. Okay, that occurs when we have x as pi over 2. Okay, then it ends up on the midline, which in this case is the x-axis. Another pi over 2 radians later at pi, it's at its minimum, the third critical point we've passed through at 3 pi over 2, and then back to the midline again at 2 pi. Okay, so between 0 and 2 pi, that's one complete cycle. It starts to repeat itself, so we know the period is 2 pi. Okay. Now the spacing of the critical points here is important. If we know the period, which in this case is just 2 pi for this function, every 1/4 of the period ends up being one of those critical points. Okay, so every 1/4 or every pi over 2 radians in this case is one of those critical points. Okay, now if we contrast that with the graph of cos of x, okay, same basic shape, same properties as far as has the same period, has the same amplitude, that kind of thing. The one difference is the graph of cos of x, since cos of 0 is actually 1. So the pattern in the points for cosine is to actually start from its max, head to its midline, and then go to its minimum, back to its midline, and then ending at another maximum. Okay, so between our initial point 0 if you will, and point 4, we've got one complete cycle, and again 4 critical points separating my starting point and my ending point. So we're kind of looking at a base sine function and a base cosine function being transformed, and various coefficients impacting what the resulting graph would look like. Okay, so in both equations that you see on this page here, the value of a, that will be representative of the vertical stretch factor. Okay, the k value has to do with horizontal stretches of the function, okay, and then your values of d and c are your horizontal and vertical translations respectively. So we can actually use the k value, from the equation, to actually help us determine what the period of the function is going to be. Okay, so in fact, if I wanted to calculate the period and I had the equation of a function, I can just take the k value and divide it into pi. The reason this works is it's actually taking the period of a base trig graph. So if it's sine or cosine, base function has a period of 2 pi, and you're really just multiplying it by 1 over k, which is the horizontal stretch factor. Okay. Another term we can relate is amplitude. One thing I want to point out with amplitude is always positive. A better thing to put here would actually be to say the absolute value of a. That way we're ignoring when a is negative. And then d would be representative of phase shift. Normally when we're talking about trig functions, we don't use the term horizontal translation. We talk in terms of a phase shift. And then lastly, the value of c corresponds, yes, to the vertical translation, but we usually relate that to the idea of what's called the midline, that being an imaginary line that divides the function in half vertically. If I want to know how far apart my critical points are, I know they occur every 1/4 of the period. So if I take the period, divide it by 4, that's how far apart my critical points are. Okay, and we are going to be graphing in radians, so keep in mind that. Okay. Another thing I'll mention that will be useful to know when graphing, and it actually ties in the amplitude and the vertical translation. If I actually want to know where the maximum and minimum points of my function are going to be, I can actually take, so the middle of my function, which is c, if I was to add the amplitude to that, that would put me at the highest point my function reaches. And similarly, for the minimum, if I start at the middle of my function, so c again, but then I subtract the amplitude, that puts me at the lowest point my function reaches. Okay, so those two formulas, if you will, are going to be useful when we get to graphing here momentarily. Okay. The focus will be on stretches for today's lesson. Okay, so for the examples we're going to try, what we want to do in each case is obviously graph the function, but it also wants us to state amplitude, period, and domain and range as well. Okay. The one thing we will not have to worry about here, because we're just focusing on stretches today, we don't have to worry about a phase shift. Phase shift will be 0 radians. And our midline will be consistent in that we don't have to move the graph up or down. Our midline will be the x-axis in each case. Okay. So what we want to do is look at that equation and establish right off the bat. We should be able to look at it and realize, okay, the amplitude is just my a value. So the amplitude of this function is 4. Okay. As far as the period goes, what I have to identify here, the 3 in my equation is actually my value of k. So since we now know formula for calculating period, period should just be 2 pi over k. So in this case, the period's 2 pi over 3. Okay. As far as domain and range, typically you could state something like that after having graphed the function, but what we want you to be able to do is actually just from the equation itself be able to come up with this. Okay. Now the domain will be pretty easy in that a trig function exists for all real values of x, at least for sine of x and cos of x. We are going to talk momentarily about some exceptions to that rule. But for a graph of sine of x or cos of x, any value of x is acceptable to enter into the function. So our domain is just simply going to be x such that x is a real number. Okay. Now the range we have to think a little bit more about, in that the range is going to be restricted because this function does not exist for all vertical values. So we're going to have y such that. Then we have to think, I should be between the minimum value for y and the maximum value for y. Now keep in mind, in this case, the midline of the function is the x-axis. So the y value there is 0. So if I apply my amplitude, I have to go 4 units below that to be at my minimum. So that would put me at -4. And then for the maximum value, I actually need to be 4 units above the x-axis. So between -4 and +4, and I'll add here at the bottom, any value on that interval that is a real number would be acceptable. Okay, so just to sort of highlight, this is actually c minus a, and what's here is c plus a. Okay, for this particular question, do realize that c is equal to 0, and obviously we already established that a was 4. Okay. So we now have domain range stated, and we didn't need to graph to do it. Okay. Now one other thing we need to sort of be clear on before we decide, okay, to graph the function is how far apart our critical points are. Okay. Now our critical points are at every 1/4 of the period. So what I have to picture is, well, I know the period is now 2 pi over 3. So we're going to have 2 pi over 3, but I have to take 1/4 of that. Okay. Now 1/4 of 2 pi over 3, an equivalent fractional representation of that would be to say, well, that's the same as saying 2 pi over 3 times 1/4. So what that would give me is 2 pi over 12. Essentially, I've just multiplied the 3 and the 4 together. I would reduce that to lowest terms. So in lowest terms, our critical points are every pi over 6. Okay. what we have to decide here is what an appropriate horizontal scale for our function should be. So here it would make sense to actually increment by this horizontally. So what I'm going to do, I'm going to just sort of set up the grid, and then we will be able to graph our points. Okay. So what I'm going to do, just so I can kind of spread out my values on the horizontal axis here. So here's my x-axis, here's my y-axis. I want to label those. Okay. So obviously, right at the center is 0, 0, where the x and y-axis cross, and then picture the first grid square here would be pi over 6. The second one I could write as 2 pi over 6. The third one would be 3 pi over 6. Fourth one would be 4 pi over 6. 5 pi over 6. 6 pi over 6, and so on. Okay, I could continue that on pretty much until I ran out of room here. Okay, and then I could also go in for negative values as well. So picture negative 2 pi over 6, negative 4 pi over 6. Okay, now one thing I want to point out here, and I might adjust the way I've written this scale. Okay, I have written this so I can clearly see sort of the increment. I know it's pi over 6 this way, but you may have noticed most of these fractions, in fact all of the fractions that I've indicated on my horizontal scale here, are fractions I could reduce. So ultimately, again, either way you want to express your scale, it's up to you. You may find it easier, though, leaving it in terms of being over 6 here, because then it emphasizes the spacing of your critical points. So I'll erase that just so it's not in the way. Okay, so now what we have to sort of realize is, well, what type of function were we graphing, or being asked to graph? So since this is asking us to do a sine function specifically, we would know, okay, well, the sine function, especially with no phase shift, will actually have a point at the origin. Okay, so I'm going to start here in just a second. I need to label my vertical scale as well. So 2, 4, 6, 8, and same thing in the negative direction. Okay, so I know this function will actually have a point at the origin. Okay. Now, based on it being a sine function with a positive lead coefficient, it's going to head towards its maximum value to start with, which we established already from the range. It's got to be at positive 4. Okay. My next point, it would have to be back on the midline, so at 2 pi over 6. It'd be back at the x-axis. At 3 pi over 6 or pi over 2, I end up being at the minimum, which is at negative 4. And then my next critical point would be back at the midline, which would be at 4 pi over 6, or that reduces to 2 pi over 3, which we recognize to be the period. Okay. At this point, we would have one complete cycle finished. Okay. However, if we insist, okay, graph 2 or 3 cycles of the function, what you'd want to do is actually just continue the pattern that we sort of started to generate here. Okay, so I would know, okay, this is the beginning of a new cycle. I could just continue on and say, okay, I'd be at maximum next, midline, minimum, midline again. There's a second completed cycle. So then if I start a third one, max, midline, minimum, midline again, and I would be done. I could also extend the graph backwards if I wished, although I'm not going to do that at this point in time. Okay, so then to actually graph this, what we'll find is we're just basically now going to connect our critical points. So there would be 3 complete cycles. At this point, the graph is done, and we will be able to move on from there. Example part B. Okay, so this time we're actually being asked to graph a cosine function, so a little different than the last one. Still want to identify the same key components at the beginning before we start. One thing that's different about this function that we did not have in the previous example was there's actually a negative lead coefficient out front. Okay, so one thing I want you to interpret, for one, the fact that it's negative is important, but what this is actually telling us is telling us that A is equal to -1. Okay, so actually recognize the numerical value that's there is important. Okay, but we also need to realize this is going to reflect in the x-axis. Okay, now when we go to state the amplitude here, I addressed this earlier. The amplitude is always a positive quantity, so I'm going to ignore the fact that A is negative and simply state, okay, my amplitude is just +1. Okay, now the period in this case, one thing we need to realize here, and this comes from inside the brackets here, we have to actually realize that K is 1/2 in this case. Alright, so that's important when we go to state what the value of the period is, because the period is actually going to be 2 pi over, in this case, 1/2. So picture dividing by 1/2 is the same as multiplying by 2 over 1. So our period actually gets larger since we have a small value of k. Our period's actually 4 pi in this case. Domain has not changed since we're still dealing with, in this case, a cosine function which is defined for all x. No change in our domain. Still all real values of x. The range in this case, so our amplitude in this case is 1. We have no vertical translation, so the midline is again still at the x-axis. So our range in this case is going to need to be, so if you think what's the minimum value, 1 unit below the x-axis, so at -1, and the maximum would have to be 1 unit above. So our range is going to have to be between -1 and +1 as a result. Okay, and then lastly, before we sort of work towards creating our graph here, our critical points, want to know how far apart they are. Well, my period in this case is 4 pi, and I know to divide that in 4. So my critical points in this case are actually pi radians apart. Okay, so what would make sense to do here, at least horizontally, our scale, if we want to increment by pi, that's fine. What we could do here is actually say, well, every second grid square could be pi, so I could say, well, the second grid square over from the origin is pi, another 2 over would be 2 pi, 3 pi, 4 pi, and so on. One other thing you might want to consider for graphing this one specifically is, because the range is actually quite narrow as far as being just between -1 and +1, what I would recommend doing here is actually vertically going up by, say, 1/2. Okay, so my vertical scale, that way I can at least see more of the function. It's not as compressed and tight to the x-axis this way. Okay, so now the horizontal and vertical scale are indicated. We can actually start to plot our points. Now, one thing to remember and realize is the type of function we're being asked to graph here. So it said in the question, y is negative cos of x over 2. So it's a cosine function. Now, the fact that we have to reflect it, which we established earlier, what you need to picture is, normally without reflection present, the function with no phase shift should actually start a cycle right on the y-axis at its maximum. However, if I reflected that, that would actually put it to its minimum instead of its max. So this function actually will start on the y-axis at its minimum, which is -1. Okay. From there, we now know the critical point spacing, so I'd be at a midline at pi. I would have to be at the maximum at 2 pi, back to my midline at 3 pi, and then ending at 4 pi. Again, reflects the fact that the period is 4 pi. Okay. At this point, if I connected those 5 points, I would have one complete cycle illustrated. What we may want to do is just continue on and show as much of the graph as possible. So that's what I'm going to do here. So there would be the graph of the cosine function we were asked to produce. Okay, for the second example today, we're going to be asked to sketch 2 cycles for the graph of y equals 2 times cosecant of x. One thing to recognize here, that is your a value. Okay, so what that means is we have to vertically stretch by factor 2. Okay. Now the one difference here, because this is one of the reciprocal functions, the process we've used for the first 2 graphs today doesn't really work in this case. We kind of need to go the more traditional route that we're used to as far as transformations of functions, and start with the base graph, in this case, which is just y equals cosecant x. Keep in mind the period of cosecant x, which we noticed the other day, was actually 2 pi. So that will be reflected in my graph here momentarily. That also means my critical points are every pi over 2. We've got pi over 2, pi, 3 pi over 2, and 2 pi. Similarly, on the other side, we can indicate negative pi over 2. Okay. Vertically, as far as how to address the scale here, I think going in increments of 1 makes sense. So every second grid square, I will indicate that. Okay, so now that our grid is set up, we would be ready to actually graph it. So what we're going to do, we're actually going to graph a base function, and then we will stretch that vertically by factor 2. One thing to remember about the graph of cosecant x is that it actually has vertical asymptotes located at regular intervals. At x equals 0, which is the y-axis, there would be one at pi, negative pi, 2 pi, and so on. So what I'm going to do, just to reflect that, I'm going to put in just a dotted line at those particular values. In between each of the vertical asymptotes, what you'll find is right in the middle is where either the minimum point or the maximum point of the given cycle is. Okay. Now there's a close connection between cosecant x and sine x. We know that, for instance, sine of x is above the x-axis between 0 and pi, so should its reciprocal graph. So as it turns out, right at pi over 2, my value of y is 1. Okay. Keep in mind as well, if you look back in the notes from the other day, the value of y when the variable x was pi over 6 was actually positive 2. And due to symmetry, right before where my asymptote is, I'd also have a point at y equals 2 when I was at the point there. Okay. From there, really that's enough. We know it goes down, makes contact at its minimum, and then has to head towards its vertical asymptote on either side. Okay. So if I went to the next interval, which is between pi and 2 pi, now what I would have to realize is, well, on that interval, since the graph of sine of x is actually underneath the x-axis between pi and 2 pi, so would the reciprocal. So as it turns out, I'm going to have a point at negative 1 where I'm at 3 pi over 2. And then similar to what we just saw in the first interval, one grid square to the right of that asymptote at pi, and one to the left of my asymptote at 2 pi would be at negative 2 vertically. And then similarly to what we had before, if I now just make the connection between the points we have here, and then add that it's going to continue to go down, we'll have graphed the next segment. Okay. As far as spacing goes, we probably could squeeze in one other section of this graph on either end. It will be a little bit tight just since we are a bit tight for space, but I would know just based on the pattern on the other side of the graph, so between pi and 2 pi, I should see that between negative pi and 0, it's going to follow the exact same pattern. So there would be the graph of y equals, we've only done so far cosecant of x. Okay. Now comes the part where, well, we were asked to do a vertical stretch of that. Okay, so that will be simple to do. Now if I take each of the points I have plotted already, when I vertically stretch them, literally all I have to do is imagine, well, what would happen if I doubled the y value that was there. So I'll just label it below. In green we have y equals 2 times cosecant of x. Okay. So example 3, what it wants us to do is come up with a possible equation. Okay. So the first one is a little easier in that it tells us some specific things. So we know it's a sine function. Amplitude being 7, literally that should just tell us a is equal to 7. Okay, and then one thing we need to realize, the period, okay, I know that I would normally calculate the period as 2 pi over k. So what we're going to do here is we're going to set our period, so 3 pi over 2, that is supposed to be equal to 2 pi over k. Now what we'll be able to do here is actually solve this for k. So if I multiply both sides by the lowest common denominator, in this case that's 2k, what I would end up getting on the left side, I'd have 3 pi k, and on the right side that would just be equal to 4 pi. I should get my k value to be 4 over 3. Okay, so it does say a possible equation here. So what we'll do, in this case, we have enough information to state the equation that we would need. So I'm going to say therefore, and because it wanted a sine function, we can go simply y equals 7, and then it will have to be sine of k times x. So in this case, 4 over 3 times x. For part B, little different. The way we're going to actually have to figure out the equation in this case is to actually interpret a graph that's given to us. And ultimately I need to figure out what its amplitude is, what its period is, and in other cases, we're not going to worry about it here. I might be looking, okay, does my function have a phase shift, and does it have a vertical translation? One thing we could do here, and I'll sort of highlight this, the point here is a maximum. So what that would make us maybe think of here is the fact that we're starting at a max on the y-axis. We could think, well, that would be, indicative of a cosine function. Okay, so in other words, our d value would be 0. Okay, there are other possible equations that will work here, but we're trying to make this as simple as possible. Okay, now what I would need to do as far as the graph is concerned, I do need to identify my amplitude. Now, easiest thing to do is picture, okay, from my midline, which in this case is the x-axis to my maximum, that would be representative of the amplitude. So my amplitude in this case is 5. Okay, now because of the fact that we're starting at a maximum on the y-axis, when we decide what our a value is, we don't need this function reflected. So what I could say is, okay, well, simply my a value should be positive. It should be positive 5. Okay. Next thing to look at is, well, what's the period of this function? Okay, so our period, we can read this directly off of the graph. So I'll use a maximum point as a reference. So if I go from my first max on the y-axis, how far do I have to go to get to my next maximum, which would be at pi? Well, that would be indicative of the period. So from 0 to pi, I've gone one complete cycle. So pi is actually my period. Okay. Now, like in example or part A, once we knew the period, we had to picture, okay, well, the period is supposed to be 2 pi over k. So pi, in this case, equals 2 pi over k. So if I was to multiply both sides here by k, we're going to get k pi equals 2 pi. Again, I can divide out the pi's. So in the end, my value of k here should just be 2. Okay, so with that in mind, I now know the amplitude, I now know my value of k. We decided that a cosine function makes the most sense to use here, so we could say therefore y equals 5 times cosine of 2x. Okay, we can discuss later on other possible options here as far as an equation, but we've kind of picked the simplest case here since we have avoided a phase shift. Okay. Okay, last example for today, example 4. Similar to the last question, at least part B, in that we have a graph to work with. Okay, it has given us the equation of this function, but notice there's no scale either horizontally or vertically to go on. What it wants us to do is actually locate the coordinates of all of the points indicated on the actual graph. So to sort of get this question started, some things we would need to keep in mind. All of the points that it's asking for are critical points, and from the equation there's a few things we can sort of establish right off the bat that are going to be helpful. Okay. So now that we know how far our critical points are apart, we know the amplitude, we know the period, we can start to label all of these points. Okay, so point B, as it turns out, first critical point to the right of the origin, so I should find that for that point the x-coordinate is pi over 4, and I know the maximum value there for y is 3. Okay, similarly, if I look at D, I know it has the same y value, but I also have to realize it is one full or one complete cycle in front of the point at B. So what I could do is envision for D that, well, whatever the x-coordinate for B was, if I add one complete period, which is pi in this case, I would be at that point. Okay, now what we would likely want to do is picture, well, rather than leaving it as pi over 4 plus pi, well, pi is equivalent to 4 pi over 4, so that will end up giving me as the coordinates there 5 pi over 4 and then 3 for the y value. Okay, for point C, that is actually 2 critical points away from the origin, so picture pi over 4 plus another pi over 4, so at point C I would actually be at pi over 2, and then since I'm on the x-axis, the y value is just 0. And then with point A, not doing this in any particular order, but with point A, I am actually one critical point to the left of the origin, so I would know my x-coordinate is negative, and I also know I'm at a minimum, so in this case my y-coordinate is negative. So the coordinates for A are going to have to be negative pi over 4 and negative 3. Okay, so we've now labeled the coordinates of all 4 points. If you have any questions, please let me know in class, and have a good day. See you later.